G'day, we're going into our second lesson into our unit on atomic structure, where today we're going to be looking at the electron and these ideas of principal quantum levels, subshells, and atomic orbitals, where our lesson objective is to understand how the electron exists in principal quantum levels and subshells, to describe the relative energies of the sp and d orbitals, and to sketch the s and p orbitals. So already there's a whole bunch of new vocabulary there that we've introduced, and we're going to introduce a lot of vocabulary today. Previous lesson, we looked at the nucleus, the protons and the neutrons. This lesson and the next couple of lessons, we're really going to look at how the electron exists and behaves in the atom. So what do we know about the arrangements of the electrons? Electrons are arranged in shells of fixed energy levels around the nucleus of the atom. These fixed energy levels are called principal quantum levels or principal quantum shells. Now, a note on this vocabulary, we're going to be introducing lots of new fancy sounding science words. The words look more daunting than they actually are. For example, quantum. All quantum means is that it is fixed or a discrete amount. So it's either one thing or it's the other thing. It can't exist within those two things. It's fixed amount. So if we look at this idea of principal quantum levels or principal quantum shells, principal, in everyday life we use the principal to mean main. Quantum, fixed, and then levels means levels. So we got the main fixed levels of energy for the electrons. The principal quantum shells are numbered based on how far from the nucleus they are. So we have our nucleus, full of the protons and neutrons that we looked at in the previous lesson. I'm just going to represent it with a black dot there. We have the first principal quantum level or the first principal quantum shell. I'm going to be using level and shell interchangeably to mean the same thing. This is n equals 1. Principal quantum level has the symbol n. This is the first one. This is n equals 1. The next shell is n equals 2. The shell after that is n equals 3. What's the shell after that? Probably work it out. N equals 4. So these are fixed energy levels that the electrons can exist in. Now, how many electrons can fit in one of these principal quantum levels is determined by how big the quantum level is. So we have a quantum level here that's got a smaller circumference than that quantum level, so that's going to hold less than that one. This one is smaller than that one, so that's going to hold less than that one, so on and so forth. And there's this rule where we can determine the number of electrons that a principal quantum level can hold. Number of electrons is equal to the 2n squared rule, where we have our n as our principal quantum level. So when n is equal to 1, we have 2 times 1 squared. We work that out. 1 squared, 1 times 1 is itself, times 2 is 2. The first principal quantum level can hold 2 electrons. The second principal quantum level, when n equals 2, this is the 2n squared, 2 times 2 squared. 2 squared is 4. 4 times 2 is 8. It can hold 8 electrons. The third principal quantum level, n, when it's 3, is 2 times 3 squared. 3 squared is 9 times 2 is 18 electrons. So we can keep doing this, plugging in our principal quantum level to determine how many electrons the principal quantum level can hold. The 2n squared rule. The electrons further from the nucleus are less tightly held, so will have more energy. We looked in our previous lesson at the idea that like charges repel each other and opposite charges attract each other. So in our atom, if we have a positively charged nucleus with all the positive protons in there, and then these are negatively charged electron shells with how many electrons on it depending on how big the shell is, the positive and the negative stabilize each other. So the closer the negative charge is to the positive charge, the more stable it will be. Consequently, the less energy it will be. Less energy means it is more stable. More energy means it's less stable. So the further we go from our nucleus, these quantum levels increase their energy because the electrons are held less tightly by the positive nucleus because they're going to be further away from the nucleus. So the further out the principal quantum level is, the higher energy that principal quantum level is. Now, this is still looking at our old atomic model, which we said last time and we're going to reiterate today. It's a very antiquated and limited model. However, we do have some useful things that we can use from it. So we're not going to completely throw it out. We're still going to bear it in mind, but we're going to look at some things in a bit more detail. So quantum theory, again, don't be put off by this word quantum. Quantum just means the amounts are fixed or discrete. So the amount can be this or that. It can't exist within this or that. It has to be one thing or the other thing. It's a quantum variable, essentially. What do I mean by that? Electrons contain energy in quanta. Quanta just is the plural of quantum. So it's only stable when they have a particular multiple of energy. And we saw that in our quantum levels. It can be this energy, or this energy, or this energy, but it can't exist within those energy levels. We'll look at why in a moment. These are called the electron shells, the energy that the electrons contain in their quanta. Electrons can move between the energy levels if they gain or lose energy. So that's what we're saying over here, that this is lower energy than this shell, is lower energy than this shell, but you can give the electrons energy so that they can move between them, so they can go increasing energy, or they can move back down where they will lose energy. But they cannot exist in between them. Now, a good analogy, I've got a picture of a ladder there. And the reason why I have a picture of a ladder there is you can think of when you climb a ladder. You can have your foot on the bottom rung. You can then increase the energy, put your foot on the next rung. You can then increase your energy, put the foot on the next rung. You can then decrease the energy, put your foot back on the previous rung. However, it is impossible for you to put your foot in between the rungs and climb the ladder. It's the same thing with the electron shells. So you can put your foot on that rung to climb it, you can put your foot on that rung to climb it, but these are discrete rungs. You can't put your foot in between these two discrete variables, i.e. the rung, and still expect to climb it. Same thing with the electrons. The electrons can be in that shell or that shell. It cannot exist in between the shells. That's what we said just before with the whiteboard. If we go in a shell closer to the nucleus, we will lose energy because these shells that are closer to the nucleus have lower energy because they're more stabilized by the positive charge of the protons in the nucleus. And conversely, we can gain or absorb energy and move up in our principal quantum levels. So our principal quantum number tells the shell's energy level, corresponds with the period of the element. Now, throughout this course, we're going to look more in depth at the periodic table, and the amount of information that you can get off the periodic table is absolutely astounding, and you just learn more and more ways to read and interpret it as you continue your chemistry education. So depending on the element or the atom that you have, the number of quantum levels that the electrons exist in will tell you what period, or in other words, what row it is on the periodic table. So far we've introduced the idea of principal quantum levels and quantum theory. They're the first two things we've looked at. Like I said, lots of vocabulary today. Don't be perturbed by it. Just they look scarier than they actually are. All right, so we can break down, if we got a principal quantum level, that word principal, that means that it's the main principal. That's what that means, so the sort of the main one. So what that implies is that, well, there's steps down that you can go. So we can break down our principal quantum levels into lower levels. We can break them down into subshells. Can split principal quantum levels further into subshells. So our next bit of vocabulary for the day. Each principal quantum level will contain a different number of subshells. And that makes sense if we think about it, because we just said that the principal quantum levels are different sizes. They're different sizes, then you can split them down different ways. They can have a different number of subshells. The subshells are given these names S, P, D, and F. All we're really concerned with in detail are S and P. We're going to sort of just talk about the idea that a D subshell exists. This F subshell also exists, but the D and the F become, increasingly and just really, really complicated. So we focus on the S and P. But these are the names of the subshells, S, P, D, and F. Next bit of vocabulary that we're introducing. In any given quantum shell, the S subshell has a lower energy than the P subshell, has a lower energy than the D subshell, and you can even say that has a lower energy than the F subshell, but we're really not going to focus on the F subshells at all. And they are different sizes. So S subshells are the smallest subshells. They can contain 2 electrons. That's how many electrons they can hold. P subshells are a bit bigger. They can hold 6. D subshells are bigger again, they can hold 10. So we've got our principal quantum level. We can work out how many electrons the principal quantum level can hold with the 2n² rule. We can then break the principal quantum level down into subshells with the S, P, D, and F subshell. And then we can sort of break that down further again into this concept of atomic orbitals. Each subshell then contains one or more atomic orbitals. An atomic orbital is a region of space around the nucleus of an atom. Now that is a very, very simple definition, and most of this lesson we're going to be talking about how the electron exists and what these atomic orbitals are. So we're going to get very, very deep into this as a concept. It can be occupied by only one or two electrons. So we have the principal quantum level. We can determine the number of electrons at the principal quantum level by the 2n² rule. We can break that down into subshells, where an S subshell can hold 2 electrons, P subshell can hold 6 electrons, D subshell can hold 10 electrons. We can break that down further into atomic orbitals, where each atomic orbital can only hold a maximum of 2 electrons. It could also hold 1 electron, so they can hold 1 or 2 electrons. What this means is that if our orbitals can only hold a maximum of 2 electrons, and our S subshell can hold 2 electrons, we're going to have 1 orbital for the S subshell. Therefore, we can probably infer that our P, if we can hold 6 electrons in the P orbital, we can hold 3 orbitals in that subshell. You can probably work out that the D is going to have 5 orbitals. So these are related to each other. We're dividing each of these by 2 because each orbital can hold 2 electrons. Okay. This is where we get into the fun stuff. Let's think about what the electron is and how the electron exists. What is it? That's the title of this slide that I've written. Understood to be one of the fundamental and elementary particles. Now, our protons and neutrons aren't considered to be fundamental and elementary particles because the protons and neutrons can be broken down even further. So the protons and neutrons are made up of these things called quarks, where you've got up quarks and down quarks in different ratios to one another to make it a proton or a neutron. The electron, I mean, as much as we can understand, the best we understand at the moment is the electron can't be broken down any further. The electron is fundamental to all particles, okay? And this can always change. So, I mean, the word atom comes from Greek for undivisible or something like that, can't be split any further. So, I mean, but we know that the atom's made up of subatomic particles. So in science, our understandings are always changing based on the evidence that's coming in, based on the research that's been doing. So who knows, they might one day find that there are these smaller things that the electrons are made up of, but as the current scientific theory understands it at the moment, the electrons are one of the fundamental particles. I like the proton and the neutron, which is made up of smaller particles called quarks. Now, when we try to understand the electron, it's very hard because it doesn't behave like matter as we understand matter to behave. When we get down to this quantum level, our understandings of how reality exists become so limited and just so different to how we experience reality on the macroscopic world, like in our everyday lives. So it can be very hard to come in with our understandings of our perception of reality and apply that to this quantum level because it just doesn't work that way. But it makes it really interesting and really cool. And this is also why our previous model, where we had the atom, where we had the atom with a nucleus with electrons orbiting like planets, that's just not at all correct to anything. A much more accurate way to describe an electron is that it exhibits properties of both particles and waves. So it exists as a wave-particle duality. What do we mean by that? The best way to describe it is acting like a standing wave. Now we're going to get into a little bit of physics here. But essentially, a standing wave is a wave with identical frequency and amplitude interfering with one another while traveling in opposite directions. What does that mean? So the standing waves will have the identical amplitude. All these waves here you can see have the same amplitude, which is from the peak to the trough of the wave. What happens is that when it's reflected off of something, the wave travels this way and then it reflects off at the identical frequency and amplitude as the previous one. Same one here. This one has 1, this one has 2. Goes down, but then it reflects off with the exact same frequency and amplitude. And what it looks like, it doesn't look like it's moving, it looks like it's standing. That's the name standing wave. But what's important about this for us is that this is a great way to think about the electron, because there's only specific nodes that a standing wave can exist at. So you can't just have a standing wave for, a continuous amount. It has to be quantized. It has to be a discrete number. There are only a discrete number of nodes that a standing wave can exist. The quanta of electrons is a lot like this. Will produce a harmonic at certain energies. We call this the harmonics of electrons. Now, another way you can get harmonics is on a guitar, and music's actually quite a good analogy here to help us understand how the electron's existing. So we have these standing waves. The standing wave here is represented by the tone of the guitar. So if we look at this standing wave number 1, this is the first standing wave that I get. So this is the lowest energy electron principal quantum level, which is just me playing the note, like so. I can put a bit of energy in that and it can go into a different principal quantum level. This is also a standing wave where I've taken that first wave here and I've just sort of split it down the middle to make another standing wave. I could put another amount of energy in it to create another standing wave, another standing wave. So every time we get a tone like that, that's representative of one of our principal quantum levels of our electrons. But why this is such a good sort of analogy is because I can't just put any amount of energy, as in where I'm getting the harmonics on the guitar. I can put I'm getting no standing wave there, I'm getting no standing wave there, no standing wave there. It's only specific amounts of energy that the electrons can exist within. So a good way to describe the electron is like this standing wave. So our analogy of the guitar with the certain frequencies of the harmonics that it can exist in. But it does have this wave-particle duality. So it's got to have some sort of characteristics of a particle as well. So let's consider an electron as a particle. And this is sort of what we were considering in our predated model, where it's circling like a planet. We were thinking of electron as a particle moving. So let's think of that, and that'll help us understand a little bit how it's existing. So we can think of it acting as a point particle, which is just a point. It has no volume, it's just a single point of negative electron point. If we took a selection of photos of an electron in an atom, we would see an electron cloud of little dots around a nucleus where the electron has been. So let's think of this. We've got an atom where we've got the nucleus, and then we've got one lonely little electron just playing by itself. I take a single snapshot of my electron at any given moment. Let's just say I have an electron there. I take a snapshot. A fraction of a moment later, I have my point particle electron there. I take it a fraction of the moment later, I have my point particle electron there. Take it a fraction of a moment later, I have my point particle of my electron there. So on and so forth. What you would end up with is a distribution of electron density in a region of space. So you would end up with this cloud of electron density, and this is what the orbital is. An orbital is a region of space, essentially an electron cloud around the nucleus of probable electron density. So it's a region in three-dimensional space where it says there's a high probability that an electron is existing in that space at any given moment. For our intents and purposes of this course, that is how we understand the atomic orbital. For now, we're going to go into it a little bit more deeper, just because I find it super interesting. Why not? What else are we going to do? So, an orbital is a region of space, an electron cloud around the nucleus of probable electron density. The shape of the orbital is determined by the quanta of the electron, so the energy that the electron has. And these are our s, p, d, and f orbitals, where these orbitals have different shapes. But it's not a particle, because I just told you that it's best described as a standing wave. So why would I tell you this model that it's acting like a particle, even though it's not a particle? It's got a particle wave duality. What's going on? What it is it's a quantized fluctuating probability wave function. What the hell does that mean? Well, this word quantized, quantum, we've looked at, it means discrete. Fluctuating is a word that you might see used in your everyday life. It means it's changing, it's moving, it's fluctuating. Probability means chance. Wave function is some math stuff to do with waves that the physicists worry about. We're not really too cared about that. So the electron is best described as a standing wave. That's what I just said in the previous slide. So essentially the orbital is the electron. So we describe the orbital as a region of space where there's probably an electron, but really the electron is the orbital itself when it's spread out in the quantum wave function state. The electron is never in a single point location. So we're sort of saying two contradicting things simultaneously. It's a particle when you take it at snapshots, but it's not a particle, it's a wave function at the same time. Essentially, it will inhabit all of the orbital all of the time, and the charge of the electron is smeared out in this region of probable electron density. So this is what I was saying before, why we can't just take our understandings of how we perceive reality and just superimpose that on the quantum level, because we need to have, essentially two contradicting ideas that we hold simultaneously that are both correct, even though they don't make sense with one another. That's why it's such a fascinating thing. But there is a probability of interacting with the electron at a single point, as it acts like a particle when it interacts with certain objects in certain ways or when it has been measured. So the electron is the orbital when it's spread out as a quantum wave function state, where the negative charge is smeared out, so it's acting like a wave. But you can interact with the electron at a single point where it's acting like a particle. Again, these two things contradict each other, but they're both simultaneously true. This leads in to what's called Heisenberg's uncertainty principle. So it's only when you measure the electron that it seems to be behaving in one spot, like I was drawing on the board just before. Before this, the particle is in a quantum superposition. A quantum superposition means that it's essentially acting as both at the same time. Again, contradicting thoughts, simultaneously correct. Now, there's a famous thought experiment by a fellow called Schrodinger, and he came up with this idea of Schrodinger's cat to help illustrate this. Now, if you're not familiar with this, what it describes very briefly is old mate Schrodinger pops a cat in a box, as you do, pops a vial of poison in there, and at any random moment, completely random, the poison's going to be released and kill the cat, right? But you have no idea when that poison's going to be released. So you seal the box up, and because it's totally random when that's going to happen, as far as you're concerned, the cat is existing in a quantum superposition. The cat is, for all intents and purposes, the cat is dead and the cat is alive simultaneously, because you have no idea which one it's going to be. It's only until you measure that, it's only until you open the box that you see that the cat is either alive or dead. So Schrodinger's cat helps us to understand this idea of the electron superposition. So what is the certainty principle? The uncertainty principle states, due to the wave-particle duality, you can only know either the position or the momentum of the electron precisely, because by measuring one, you will be changing the other. If you measure the electron's momentum, as in its speed, its movement, you will see it behaving as a wave. However, by measuring its momentum, through that very method, you have to have changed the particle's position. So converse to that, if you measure the electron's position, you will see it behaving as a particle. This is this idea of uncertainty, the fact that you can never be certain for sure both its momentum and both its position, and consequently if you measure one, you'll change the other, so you'll see it behaving as a wave or see it behaving as a particle depending on which one you change. Now there's the good way to remember this is there's the classic joke of there's an electron driving down a highway and a policeman pulls it over, and electron pulls over, the policeman goes up and goes, "Sir, do you realize you were going 180 zone?" The electron goes, "Great, now I'm lost." So Heisenberg's uncertainty principle. So bearing all that in mind, the atomic orbitals of an electron are simultaneously regions of probable electron density, where there's a high probability the electron will be in any given space of that region at any given time, whilst also simultaneously the orbitals of the electron itself spread out, where it's smearing the electron charge across this region in a quantum wave function. Wave-particle duality. But as I said before, for our intents and purposes of these courses, we're going to understand the orbital as a region of space around the nucleus of probable electron density. Now, let's go back to these numbers, the s, p, d, and f orbitals. We said before an orbital can hold either 1 or 2 electrons each. The geometry of the orbitals is going to depend on the energy of the subshell that they are in and how they stack up on top of one another. So to recap everything just briefly, we said we have at the very top the principal quantum level or quantum shell. How do you spell? I can't spell. Quantum shell. Now this is the main energy level, which is our old atomic model. So we have quantum level 1, quantum level 2, quantum level 3, etc., where that's low energy, more energy going out. Now each of these can only hold a certain amount of electrons. That can hold 2, that can hold 8, that can hold 18. We can break the principal quantum level down into smaller ones called subshells. So each of these quantum levels, depending on how many electrons it will have, can have an s, a p, a d, and then an f orbital, but we're not too concerned about the f orbital. S orbitals can hold 2 electrons, p orbitals can hold 6 electrons, d orbitals can hold 10 electrons. So what you might be noticing here is there's some numbers that are sort of corresponding to the quantum shell. Our first one can hold 2 electrons, so it's going to have one s subshell to hold those 2 electrons. Our second one can hold 8, but what you might notice here is that 2 plus 6 is equaling 8. So these two are very tightly linked. And then with the subshells, we have the atomic orbitals. I cannot spell today to save my life. The orbitals can hold 1 electron or 2 electrons, and that's it. So depending on how many subshells there are will depend on how many orbitals. If it can hold 2 electrons, our s subshell has 1 orbital, our p subshell has 3 orbitals, our d subshell has 5 orbitals. Let's look at the 2 orbitals that we really care about, the s and the p. The s orbital is the simplest orbital. It is just a spherical shape. Only one s orbital for each principal quantum level, as the s subshell can hold 2 electrons. So thinking back to one of the reasons why our previous model was so limited was, well, this is only showing things occurring in 2-dimensional space. But look around us, we know that reality exists in 3-dimensional space. So we can make this model more accurate by including the 3rd dimension into the model. So instead of just the x and the y axis, we now introduce this z axis. So this z axis is coming into and going out of the page to show that 3 dimensions. We can think of this being the simplest orbital. Let's say we got 2 electrons in one of our s orbitals. Electrons have negative charges repel each other, like charges repel. So these electrons are going to want to be as far away from each other in 3-dimensional space as they can be if they're both in there. Now, there's no other, if S is the first subshell that we're filling up, there's no other electrons there. So we can sort of model this with balloons. So in 3-dimensional space, the furthest things can be away from each other while still being held by the nucleus, which would be at the center of the balloon here, is just in a spherical. Okay, bear that in mind when we consider the p orbitals on this next slide. The p orbital is slightly more complicated because our region of the lowest energy closest to the nucleus has been taken up by the s subshells that are beneath it. So all electrons, if we've got more than 2 electrons, they've got to keep stacking on top of each other. However, this sort of region of negative space is now taken. So the electrons, other electrons being negative, aren't going to want to just get in there with it. So when we stack on top of an s orbital, the p orbitals end up making this dumbbell figure 8 type shape, where one of these p orbitals, this whole thing is the p orbital, these 2 lobes is all one p orbital, and this can hold 2 electrons. So we can think of this in 3-dimensional space by tying 2 balloons together, like so. So we have the s orbital that exists sort of underneath this in the center of this one here, and then if the p orbital has to fill on top of it, we will get our dumbbells like that. So because we have 6 electrons that the p orbital can, that the p subshell, can hold. Each orbital can hold 2 electrons, so we need 3 p orbitals, which in 3-dimensional space is going to look like this. We're going to have 1 orbital on the x-axis, like so. So that's the p orbital on the x-axis. Now, you can also have a p orbital on the y-axis. That's my blue one, p orbital on the y-axis. And then you can have a p orbital on the z-axis. So that's going into the board and coming out of the board. So when they're all on top of each other like that, it looks a little bit complicated. All right, pz here. But this is why I show the balloons. So if we consider all 3 of the p orbitals together. Now, each one of these colors is one p orbital. One p orbital can hold 2 electrons. The p subshell can hold 6 electrons. Now, this sort of makes sense. What happened to my other balloon here? If our simplest electron cloud is just a sphere, as we can see here, that's the furthest our balloon can get away from itself, it's just a sphere. But if we build on top of that, this sphere is sort of high, is sitting in the center there. It's sitting beneath these other orbitals, where it's going to be just in the center like that. That's our S orbital. So the next sort of shape that the electrons can take to give it the lowest energy is this. And we can see this as if we've got, let's say that this p orbital is full, so there's 2 electrons in each of these p orbitals. In 3-dimensional space, the furthest the electron clouds can be from each other is in this conformation. That's the furthest the balloons can get away from each other. So as the electron clouds become bigger and bigger and we go into those d and even those f orbitals, they have to become super complicated, and there's multiple shapes they can take in order for them to have that lowest energy conformation that they can have. Now that's, if you ever get lost in any of chemistry really, you just got to remember that everything just wants to exist in the lowest energy conformation that it can. That's why any sort of matter exists, or why any reactions take place or anything happens. So the reason why it makes this shape is because this is the lowest energy conformation that you can have in 3-dimensional space once you've filled an s orbital underneath it. 3 p orbitals have this dumbbell figure px, py, and pz. So let me just show you that on 3 separate axes before we finish up for today's lesson. So if we have the pink can be, or the red can be the py, because that p orbital is on the y-axis. Then we'll have black on the px, dumbbell shape, px. And then we will have blue on the z-axis, pz. If we put them all together, we get this. So my pink is my py, 2 lobes, 1 orbital can hold 2 electrons. Then the yellow can be the px, like that. And then the blue, the green are the pz. So you can see this z-axis is when it's coming in and going out the back. So 3-dimensional space. And then to recap, our s orbital is a very simple sphere like so. Okay, and that concludes the lesson. What have we done? We have described the number and relative energies of the s, p, and d orbitals for the principal quantum numbers 1, 2, and 3, and also the 4s and 4p orbitals. And we've described and sketched the shapes of the s and the p orbitals. These are the tasks that you can do to consolidate this lesson. Pause and work through those if you so wish. All right, we're going to keep looking at the electron for the next couple of lessons and how it exists within the atom. But that's all for now. See you later. Have a good one.